Hi. Again, I am making one video. So here I will explain you step by step procedure. So first of all, you have to set all the parameters. See here I have set all the parameters. Huh? You can copy all these things. You can keep the same thing for the first simulation so that you will get the correct results. Then in the component 1, you have to draw one geometry. So under geometry, I have inserted rectangle which has dimensions 0.1 meter is width and zero point 0.1 meter is height. So this is my geometry, right? So after that, as I have selected already the physics, but before that we will add one blank material. So from the material you have to go to add blank material, and under this you will have to insert some properties, right? So what properties will be needed? Thermal conductivity, which is already defined in the parameters as a K0, density, rho 0, and heat capacity at constant pressure, that is Cp0. Right? These all values I have already mentioned in the parameters toolbox. You can see K0 zero point 0.2 watt per meter Kelvin, Cp0 1000, and rho 0 1100. Right? So these are my material properties. After this material and geometry, we will go to the physics. Heat transfer in solids. So under this there will be some equation. You can go through it for your understanding purpose. See here in heat conduction in solid, you have to add the thermal conductivity, which is from the material which we have added. Density is also from material, and specific heat also from the material. Right? Again, come to the initial value. So here initially you can keep some low temperature like 300 Kelvin or something like that, right? Now I am simulating this is for isothermal condition. That's why I have kept the initial temperature and the mold temperature as same. No, some difference in there, 413 Kelvin. Right? But at the start, you can go for like 300 Kelvin as initial temperature, and the mold temperature as like 400 or 413 Kelvin. Right? So initial temperature value means for all domain, right? And thermal insulation just it's, by default it will be overridden with this mole temperature, and this mole temperature will be for all boundaries. This you have to select. Huh? So this is for all the boundaries. Then comes the heat source term. So under this heat source, material is a solid type. So you have to come to the general source, which is user defined value, and this is our equation, that is minus H underscore R is the heat of reaction into d alpha by dt. Right? This is our transient term. Right? So this is all about the heat transfer in solid physics. Once you will finish this, come to the domain ODEs and DAs. So here you have to insert the ODE equation, right? So here I am using the Kamal and Sorer's model, autocatalytic model, right? So you can add any model here, whichever you want to use, and Herder model or modified forms of these models, right? So, but you have to appropriately write the equation, right? So this is a Kamal and Sorer's model. Okay, all these parameters at M1, M2, A1, A2, everything I have mentioned in the parameter. After this, come to the initial value, that alpha. Here you can keep 0 value, but this model is quite complex. So just for the sake of like simulating, because this model doesn't understand anything, right? Whatever you provide, it will come. So if you sometime if we give the value 0 or close to 0, there is a difference, right? So that's why like 1e minus 7, which is close to 0, but there is some value that I have kept here. You can mention there should have a 0 value, but just for the simulating purpose, I have mentioned it as a 1e minus 7. That's all about these two physics. Now come to the meshing. So meshing is also one if you have to explore this phenomena. So here physics controlled mesh I have done, and element size is fine, right? That's all. Then we have to go to the study. Under this study, it will come time dependent, and we have to simulate it. So I am simulating um, from 0 to 4000 second with a step size of 1 second. And these two physics I am solving it. Transparency solid and domain ODEs and DEs. These are the green mark. Right? This I have already simulated, so again I will not simulate, otherwise it will take more time. Right? So I will directly go to the result section. So under this result section, we'll go to this temperature HT. So here you will see at the time of 60 seconds, you will see surface temperature, right? So at the boundary, the temperature is around 412 Kelvin, and then at the middle, it is like around 396 Kelvin, right? So this is just for 60 seconds. So we'll increase time. We'll see at the end of 4000 second what can be the temperature, right? So yeah, so the temperature gradient is reducing, right? Like the difference is from 340 Kelvin to 410 Kelvin, right? Actually, this initial value, I think by default, like by mistake, I have kept it there. The initial value was 300 Kelvin only. Maybe after running the simulation, I have kept this value, right? So you don't go with this initial value. No? Right. Now, as thermal contour, just contour plots. I will not go for more second. Now we'll go for the degree of pure contour plot. So see, at the end of 4000 second, this dependent variable, right? Alpha value. So this very dark value, na? Like close to 0 point, more than 0.95 value, you will see. Right? At the center, the value is 0.7. Right? Means it is reaching to the point one, reaching to one value. If you will see for like initial time, like around 60 second or something like 40 second. If I plot it, they see, you will see at the boundary the value is like 7 to the power minus 2. The value is very less. So the curing reaction has started, just started, right? Value is very less. And if we increase time with respect to time, like around 2674 second, yeah, right? So the recurring reaction is start value is increasing. That's it. Now this is all about the contour plots. Now we'll go for the one-dimensional plot. So you know how to plot it. So I will directly go there. So here if you'll see, the expression is alpha, right? Alpha versus time, which is in minute. And if you see the value around like 60 minutes, value is 0.0 to 0.7. So to reach up to one value, you need to run the simulation for more time. That's it. So this is for the degree of pure plot. Similarly, if you can plot for the temperature, so here from here I can change the expression, or you can insert another one-dimensional plot. So better I will add another 1D plot so that you will know no, how to do it, right? So under the result section, go for 1D plot. Right here point graph. So under this point the temperature is already there and your time will be in the minute, right? So I will I have to select now at which point I have to. So here under the data set I have selected one cut point 2D1, so which is at 0.05. At the center I have, you can plot anywhere so that you will get the idea, right? More plots you can club together at a once. I will also show that you. But before that, we will plot this. Oh, sorry, I have not selected it, so it will come blank plot. See, it came blank plot. Why? Because the selection is like data set is parent. So it will not. So we have to select cut point 2D1 and then plot. So the temperature here is decreasing from 400 to 330 Kelvin. This should not happen. What can be the reason now here? Yeah, this you have to explore. Right? In next video, I will explain this to you as well. Right? So yeah, now how to club the plots. Na? So here we'll go to one more cut point. So cut point 2D, and we'll select the coordinate as like 0.05 as x coordinate and y coordinate 0.01 is the point comes. So the point is here now, right? So now we club the 2 points. So again here I will add one more point graph, right? And this point graph will be for cut point 2D2, and remember we have to change the expression to degree of cure here. The previous plot is of degree of cure, right? So again we'll go for legend. We have to mention the legends so that we'll get to know, right? So we have two plots now. Oh, this plot is for second, this plot is minute. So we have to come for the minute. See, right? So if you see, this has like value up to 1. Why? Because this point is nearest to the boundary point. That's why that value is reaching to 1 very fast compared to this. So like this you can do the comparison. So that's all from my side. So you can explore this exercise, and you can simulate for more like complex geometries. Okay.